share my screen. Okay. Hi, I'm Sean Sullivan. I am the Vice President of what we call the Design Pillar at Engineering Industries Excellence. I will be joined by John Olson, a pre-sales solution consultant who's the real brains of the outfit here. He'll take over when it gets real complicated. So we are talking to you today because the battery development direction is moving towards battery safety improvements to mitigate hazardous phenomena like thermal runaway. At the same time, battery performance improvement is a key to ensure the electrical vehicle's success. We need to keep it affordable, improve the battery lifetime, leverage the connectivity and digitalization trends as well. Moreover, new cell generation is part of this global trend, whether to improve the cell's performance or to improve the safety with solid-state electrolytes, for instance. And with this increased demand of electrical vehicles, the manufacturing capacity increases as well, while moving towards a sustainable value chain. So we have a number of challenges from these global trends. Battery development is facing a measured challenges to comply with quality standards, to meet the safety, the performance, and lifetime compliance standards. This is all within a short design cycle and while minimizing cost. This slide is not exhaustive, but the question here is the following: how to address these challenges? There are multi-scale and multi-physics simulation and testing possibilities, starting from the molecular scale to the cell level, to the pack and the vehicle level, including different subsystems and controls. SimCenter provides an integrated workflow solution to address battery development challenges at the very different process steps while connecting all the activities. You start from the criteria at each level, and it follows a streamlined multi-physics simulation and testing workflow. The objective here is to meet the requirements at the different stages. The output of each stage becomes an input for the following stage. In this webinar, we're going to focus on the pack development level, and more specifically, the integrated workflow to address design optimization, then system integration with controls. The focus on this webinar is the pack development level, so here's the agenda. First, we're going to present to you the pack design optimization workflow to meet the safety requirements. Then we will present to you the system integration with controls to meet the battery performance and limit cell aging. All right, let's take a look at one of the biggest challenges in modern battery design. That is the combination of safety versus energy density. Two opposed things. The more energy density we get, the safer it's gonna, the less safe it's gonna become, correct? Is safety the price we must pay for high range and performance in electrical vehicles? The answer is no. Safe battery packs are possible for cell chemistries with high energy densities if the safety considerations are considered early in the design process. It is possible to achieve safe batteries on the pack level only if it's done early in the design process. How can this be realized? Well, John and I are going to like to show you that in today's webinar. So the worst case scenario that can happen in a battery cell is the thermal runaway. It is a summary of several exothermic reactions that start if the cell has received the required activation energy during a thermal runaway event. The cell releases large amounts of heat and hot vented gases that can reach temperatures over 1,000 degrees Celsius. The mechanisms that trigger thermal runaway are overheating, mechanical destruction, or the short circuiting of the cell. The short circuiting can happen externally over the cell tabs or internally. For example, if a nail penetration test is used during which the nail penetrates the positive and negative electrodes of the cell. During the thermal runaway event, a lot of complex chemical reactions happen inside the battery. SimCenter Star CCM Plus offers a simple workflow to model the heat release in the cell venting during the propagation. In this approach, the total heat released by the cell is divided into two mechanisms. The first one is the heat is released by the venting gas. The second one is the heat that is released by the solid parts of the cell. The simulation parameters required as an input are based on an accelerated rate calibration test. We will refer to this as the ARC test. During an ARC test, the cell is placed inside a test chamber and triggered into thermal runaway. This can be done by any of the previously described trigger mechanisms, overheating, short-circuiting, or by nail penetration. Based on the output data of the ARC test, the parameters that are required as simulation input can be calculated and stored in two tables. The first table contains a heat rate over the cell temperature, and it describes the heat that is released by the solid cell parts. The second table contains time-dependent mass flow and temperature values of the venting gas. Here's a short example of how the heat inputs can be applied inside Star CCM Plus. The picture shows a single prismatic battery cell that is surrounded by air. On top of the cell is a safety vent. The start of the gas release can be made dependent on a condition. For example, the temperature of the cell stack or the temperature of the cell casing. Once activated, the program interpolates through the table in which the mass flow rate and the temperature are defined over the venting time. For the heat that is released by the solid parts, a new feature in Star CCM Plus is now available and helps you to simplify the setup. The new feature that can be used to model the heat that is released by the solid cell parts is called the thermal runaway heat release model. It is part of the user-defined battery model inside Star CCM Plus. The start of the heat release is controlled by a model activation constraints in the form of field functions. The new thermal runaway heat release model can be combined with an equivalent circuit model for electrothermal simulations. This enables the user to develop battery packs and work on the thermal runaway and electrothermal simulations in one simulation environment. I would like to demonstrate to you the advantage of such a combined setup with practical examples. The first use case for thermal runaway is a single battery pack of 6 cells, and we need to ensure a sufficient passive thermal runaway protection. The second use case is to simulate a light-duty test cycle procedure and determine the required cooling system parameters during the light-duty cell test cycle. And finally, we must generate training data that can be used to train a fast-running neural network model. So each bell battery is composed of multiple solid parts such as casing, positive and negative thermals, vent valve, safety valve, insulation plates, and connectors. The battery cells are separated from each other by 5 heat shields. The task is to ensure passive thermal runaway protection. The worst case scenario for battery pack is a chain reaction of multiple cells going into thermal runaway in a short amount of time. This would create too much heat and too much pressure than the battery casing or the battery venting system could handle. Once a battery cell receives the activated energy that starts the exothermic reactions, the thermal runaway cannot be stopped. So it's not worth trying to stop a single cell. A better strategy is to slow the propagation between the single cells down so that the heat generated and the pressure caused by the venting gas is not released at once, but in small amounts for each battery cell. In combination with the heat-resistant battery casing and an effective venting system, this could decrease the risk to a minimum. Materials with high heat resistance and low thermal conductivity are also known as heat shields. We plan to place heat shields between the battery cells, and we want to use SimCenter star CCM Plus to identify the required thickness. The requirements for thermal runaway safety depend on the industry sector, and they cannot be generalized as a free-defined safety criteria. For our purposes, we require a time span of 90 seconds between the first cell propagation and the last cell propagation on the module level. This is just an example, but we show here a parametric workflow and the requirements that you have that can be adapted to your specific case. The thickness of the heat shields can have a very big impact on the overall size of the battery and its parts. At this point, the battery geometry is set up completely parametric for the heat shield thickness in the Y direction. We contacted a heat shield supplier, which offers heat shields in 3 different thickness classes: 1 millimeter, 3 millimeter, and 6 millimeter. Thermal runaway analysis is performed on a module level. Therefore, the input parameters for the heat release of the solid cell parts and the venting are set up like it has been shown to model the reflection of the vented gas from the cells. The distance between the cell tops to the upper surface of the air region is equal to the equal distance between the cell tops and the battery lid you see in the picture on the upper right. We simulate one module that is surrounded by air, and the air region has a wall boundary condition on top. So this part of the air is behaving like a wall. We do that because we want the model to reflect the hot venting gases from the battery lid to the neighboring cells. This has a big impact because the vented gases can have temperatures over 1,000 degrees Celsius. We want to include this additional heat in our thermal simulation. This video displays what thermal runaway looks like in a full battery. So let's take a look at the results from the first simulation for a battery module with 1 millimeter heat shield thickness. For this thermal runaway case, the first cell is heated up until it reaches the temperature. When it starts the thermal runaway, this temperature will be called the trigger temperature. In the following, the value that you see here, which is called Tmax, describes the maximum time between the first cell and the last cell that go into thermal runaway. The first cell, which is heated up until it propagates, and the last cell that goes into thermal runaway is usually the cell that has the furthest distance from the trigger cell. So in this case, we could see that the maximum time between the first and the last cell propagation in the pack equals 50 seconds. Our requirement is at least 90 seconds. So this configuration didn't pass the test according to our safety criteria. So this is again critical because we have too many cells that propagate in a short amount of time, which will release too much heat. We consider this design as not safe. It could lead to an explosion of the whole module. In the next design, we increased the heat shield thickness to 3 millimeters, and we repeated the simulation. The max time between the first and the last cell has now increased by 38%, which is good, but the maximum time, which is now 69 seconds, is still not high enough to fulfill our safety criteria of 90 seconds between the first and last cell. Finally, the last configuration is with 6 millimeter heat shield thickness. All requirements are fulfilled. The maximum time between the first and last propagation is now 99 seconds, which is above our required value of 90 seconds. Imagine that the vented gas that is released by the battery cells must go through the burst disc out of the battery casing so that the pressure can be released. Here, the risk that the pack is closed is very low, and this is now the safety design that we identified by our design exploration in star CCM Plus. We have sufficient time between the single cell propagations, and now the heat shields provide a safe battery pack in combination with the heat-resistant battery casing and an efficient venting system. Here again is an overview of what has been achieved. And you see how the percent increase between the different heat shield thicknesses influences the max time span between the propagation of the first cell and the last cell of the module. After we finalize the design for passive thermal runaway protection, we can continue with another use case of thermal management. In this case, the battery pack consists of 2 modules cooled. We will run the worldwide harmonized light-duty test cycle on the battery and look at the effects of varying coolant flow rate and temperature. To set up electrical circuits inside STAR CCM+, the circuit editor is used to create connections which join the 2 modules in parallel of a table that runs the light-duty test cycle on the battery pack. This is a classic dynamometer test for the determination of emissions and fuel consumption by light-duty vehicles. We identified the required cooling system parameters, and 6 simulations are performed with STAR CCM+. The first 3 simulations keep the inlet temperature constant and vary the mass flow rate at the inlets. The other 3 simulations keep the inlet mass flow rate constant and vary the fluid inlet temperature. This video shows the temperature profile of the cells while experiencing the light-duty test cycle. On the plot on the left, you see the current during the light-duty cycle, while the plot on the right shows the state of charge. On the left, you see with the flow rate varied, the temperatures of the cell stacks stay in a range between 39.4 and 39.9 degrees Celsius, while we vary the inlet flow rate. The plot on the right, however, shows that the coolant temperature varied. The result is a temperature range of 34.6 and 39.9 degrees Celsius, showing that the coolant temperature has a much greater effect on this set of tests. At this point, I would like to hand the presentation over to my colleague, John Wilson, for the remainder of the presentation.
All right, thanks, Sean. Let me go ahead and share my screen now, and I'll start where you left off. All right. It looks to me like y'all are able to see this. Does it look okay? All right. Hopefully that's a yes, so I'll just keep on going. So 3D transient analyses like the one that was just shown by Sean can sometimes take many hours to complete, or even days, depending on the hardware available to the user, the physics setup, and of course the mesh count. While this kind of simulation does provide a high level of spatial resolution that can't be observed in any other type of test, it can often be beneficial to use a faster lumped parameter approach to explore the effect of various conditions on pack or cell thermal runaway or during nominal operating conditions. Simpson or AIMSIM allows the user to, once parameters and boundary conditions have been properly defined, simulate thermal runaway, which we'll talk about first, by solving a set of Arrhenius equations. And the analyst can use this model to even understand the amount and origin of released gas during thermal runaway. On this plot here, which is comes from an AIMSIM simulation, you can see at the final time point of 120 times 10 to the 3 seconds, the largest amount of gas that's present in the system can be attributed to ejection from the battery vent. If we now go to this lower time point, you can see at that particular point in time, The amount of gas that's present in the system is a result of negative decomposition, which is a process that occurs during thermal runaway. The effect of state of charge, or SOC, can also be studied. Here we see SOC does have an effect on the onset of thermal runaway, but not necessarily on the peak temperature or thermal profile. So here we have a cell with an SOC of 100%. It goes into thermal runaway before the cell that's at an SOC of 50%. So there's a lag in time here. Similarly, we can look at state of health. So we look at a newer cell with a state of health of 100%, and then an aged cell at an SOH of 90%. There's a similar story here. You can see that the newer cell goes into thermal runaway first, followed by the aged cell. These are just a few examples of the virtual tests that you can run to understand the effect of different operating conditions. Once that's done, you can actually use these data that you simulated within SimSim or AimSim, in particular the venting flow rate and temperature versus time, and then of course the heat released by the solid cell. And you can take that information and import it into star CCM+, which is the 3D solver, so that you can run your model, simulate these processes in 3D, which of course you'll get more spatial resolution, but it'll take longer, right? So instead of actually running an accelerated rate calorimetry test here, it's theoretically possible to simulate that data within SimSim or AimSim, and then plug it into star CCM+ as the boundary conditions. Now I'd like to shift our focus to battery pack model reduction, which can provide not only additional insight, but also save on computational time. So modeling the 3D thermal behavior of a battery pack, especially when coupling the electrical and thermal solutions in a transient manner, like Sean showed you in the cold plate example of that battery pack, it can sometimes be nonlinear. So generating a table versus time from 3D and then mapping that, using that as a data mapper in your system simulation model, it may not be sufficient. So that's why we like, for these complex physics type of problems, to use a reduced order model. So in the 3D model, you can get, of course, local hotspots in the pack when you consider the actual geometry, but the time, again, can be long to run these cases. And using SimSim or reduced order modeling, you can run a selection of 3D simulations and feed that data into software to build a reduced order model that can quickly get physically relevant and accurate results within seconds. And I'd like to go into a demo of SimSim or reduced order modeling here. So you open the software. Essentially, you then add the data that you've generated from SimSim or star CCM+. It's in CSV format. You import it. In this dialog box, you just make sure everything is properly formatted and you have the columns and everything in the right order. It loads the data up into the software. You can choose which data sets you use for training, which data sets you use for validation. And you can leverage the model sweep to apply different types of models. So here we have an option of a neural network, response surface model, or a Gaussian process. And we compare all of these different models. And you can quickly check the fidelity of each. How do they compare to your simulated data, your high fidelity simulated data that you've imported into the software? You can kind of look at linear collinear relationships to determine, if the model is suitable. And then once this model has been created, you can then go ahead and export it out as a neural network model, or whichever type of training model you chose. And then when we've generated this model, you can then essentially import it into into SimCenter AimSim to be a component of that particular network. And that's what we're going to show right here. So you've got your larger network model in SimCenter AimSim, but we're now exporting it, exporting this ROM to take the place of a component within there. And that's what we see here with our reduced order model in the simulation environment of SimCenter AimSim. And so rather than coupling at that particular level right here with a 3D simulation that takes a long time, you can actually add in the data from this SimCenter reduced order model that essentially takes the place of that, right? You're still getting that high level of fidelity, but it takes a much smaller amount of time. And this is just an example of these plots right here. You can see that the results from the ROM, reduced order model, match up quite well to the 3D simulation data. And the CPU time was only 0.04 seconds for 2200 seconds of fast charge. In summary, Sean and I have shown you how you can address several challenges through this model approach, including satisfying safety compliance standards, making sure that the battery lasts long enough, and one of the most important factors of reducing the design cycle time and development cost. We're able to model the complexity of these battery problems that involve not only continuum physics, but also electrical. And most importantly, all of these technologies are continually developed, and we provide support and adoption through your use of them. With that, I'll conclude my portion of the presentation, and thank you for your time.
All right, so we have a few questions that came in from the audience. Sean, this first one's for you. It's in regard to the thermal runaway part of the presentation, and you showed how a cell on the end fails first and how to model out thermal runaway. How could you handle, or how would that approach in software handle a cell in the middle failing first?
Well, that's a very good question. I imagine that it would not meet the criteria. And I'd love to run it and get back to the audience or whoever asked the question with the answer. It was an excellent question.
Great. Okay, so you'll run it through and oh, go ahead, John.
Oh, I was just going to say regarding that question, I think it was from Robert, right?
Mm-hmm. It was.
Yes. Yeah. So I think the answer to that is, in part, you do assume that the cell on the end fails first. That's by the user defining essentially the location of the cell that fails. So you could actually model a cell in the middle failing by introducing a heat source there. And then, the thermal runaway phenomena would propagate from that middle cell. And then it would, at some point you'd stop seeing cells going into thermal runaway. And at that point, that would be the last cell that fails.
Okay, good. Sean, another question for you. What kind of test data is required for the 3D thermal runaway simulation?
The ARC test that we went through, that's the data that needs to be acquired for both the venting and the solid contributions to the thermal runaway.
Mm-hmm. Okay, great. And just scrolling through the questions, here's another one for Sean. Sean, what types of learning models were used in the demo you gave in the SimCenter reduced order modeling?
Yeah, so that was the last part. That was part of the last section of the presentation we just gave. But essentially, there were the options of Gaussian, neural network, and response surface models.
Right, so 3 really good questions. If the audience has any more questions, you can send it to the chat before we wrap up, or certainly you can contact us and we'll get back to you with any answers to your questions. So maybe we'll give a minute for the audience to just add any more questions to the chat.
Yeah, thank you, Sean, John, and Kevin for the presenting today and taking the time to answer some of the questions. I'm sure that there will be more coming in. So if it is, feel free to contact us and we will answer all your questions through the email. The recording of this webinar will be available on demand within 24 to 48 hours. I will try to get it as soon as for you, and you will receive an email with the link to view the recording. And in the meantime, if you think of any additional questions, just feel free to contact Sean and John at their email in the bio. We would like to, encourage you to visit our website, sw.siemens.com. There you will find more software and learn more about the solution we're offering. And don't forget to register to sign up for the upcoming section on December for the battery design and development with digital twin. All right. Finally, if you have a project immediately in mind, you can give it a call directly. The QR code will take you to the list of the company phone number there that you can find your location and give up a call to talk about your project. All right. And with this concludes our today's webinar. Thank you for attending and have a great day,
Lynn,
everyone. Bye-bye.
Before we go, Lynn, there's one more question.
Yes.
Sean,
awesome. Please go for it.
Can you model non-ideal behavior like cell vents not working?
Yes, of course. Yeah.
Yeah, so
lots of flexibility.
Yeah, I think, the cell venting is triggered by a certain temperature or field function that you write into in the context of Simpson, the 3D world, Simpson or star CCM+. If you wanted to model the non-ideal behavior, you could essentially set that cell that you want to be the non-ideal one not to vent. But furthermore, star CCM+ has several multiphysics capabilities where you could even essentially use fluid structure interaction maybe to model that pressure building up and then the deformation of the battery cell itself. So there's a lot of different ways we can look at tackling that problem.
Great. All right, with that, I think we're done with questions. And Lynn, you're about to close, but why don't you do that one more time?
Yeah, no, thank you. Thank you for all the questions. Oh, and saw that there's another one coming from Lucas. Do we still have time? Okay. Yes, if you go ahead, Kevin and Sean and John, with the last question here from Lucas.
Great. Thank you, Lucas, for your question. What results have you seen with thermal runaway and propagation regarding sodium ion?
To be honest with you, I've only worked with cases where we're looking at lithium ion thermal runaway, but we are investigating, right now our our ability to explore, kind of more exotic battery, I guess you could say, technologies like sodium ion. So this might be one of the questions, that we're working on now, but I can also check with some of our application specialists to get back with you, Lucas, on that. So.
Okay, great. We'll follow up. Another question. During the thermal runaway event, the generated heat moves the neighboring cells dissipated through venting gas and convected from the body to the air. How is the last term, convected heat transfer coefficient, captured in the software?
Yes, so essentially we when we model conjugate heat transfer in star CCM+, you'll have a solid interfacing with the air, right? And we don't actually need the heat transfer coefficient there at that interface. We actually use the boundary condition that the temperature on one side essentially equals the temperature on the other. And so you don't need a heat transfer coefficient at that point. If you're directly connecting the solid and you're directly connecting the air boundary. If you're looking at the surrounding air, you know, the ambient air, then you could apply some kind of convective boundary condition that you would get some data for, you know, the atmosphere essentially. If you know, to account for any other heat transfer further afield.
Great. Okay, I think that's all the questions we have today, and we'll follow up on the one from Lucas and a few others.
Awesome. Thank you so much, everyone. And we will send you the recording in the next 24 to 48 hours. And remember, if you have any further questions, just email it to, just send an email to Sean and John, and we will be sure to answering your questions. All right. With that, everyone have a good day. Bye-bye.